been here before, and on this August day, welcome you everyone. I hope that you'll stay. Today our speaker is Harmony Zhan from York University. Let's see if she can tell us about discrete quantum walls and how to decompose them into continuous quantum walls.
Thank you very much, Sophia. That was nice. And thank you everyone for coming today, despite it's a holiday. And also, I made a little change to my title because I realized decomposing quantum walks has some other meaning. So I changed it to factoring. Okay, anyway, today I want to share with you a discovery I made last week. I think it's a little result, but it ties nicely a continuous quantum walks into discrete walk, or the other way, like whichever way you prefer it. So I hope after today's talk, more people will get interested in discrete quantum walks. Okay, and here is a plan. Unlike a continuous quantum walk, there are so many models about discrete quantum walks. So I will first start by explaining why, and give you some background on a specific type of discrete walk called verbal walk. Okay, and then after that, I'm gonna take a logarithm of the walk. This will become the bridge between the continuous world and the discrete world. And then I will just focus on the distance regular graph as the underlying graph, because so far that's the only class of graph that I can prove some results about. And finally, I'm going to show you on a distance regular graph, I can factor my global discrete walk into a bunch of continuous walk. Moreover, each of these walk are on the some distance digraphs of the line diagram. Okay, so that is the plan. Okay, so here is a path on 3 vertices. For some reason, it has become our favorite graph in the past few weeks. So I decided it's a good example to show you why discrete walk is different from continuous walks. So here we have its adjacency matrix. Okay. And from last week, Chris's talk, we know that in a continuous walk, the transition matrix at any time t is the exponential of I times t times this adjacency matrix. Okay. So by this form, we know that the property of the walk naturally reduces to the property of the graph, or to be more precise, we are looking at some spectral properties of A. Okay, so that makes sense. But now in a discrete walk, things change. So the first change you make is the time t can no longer be any real number. It has to be an integer. So let me use k to denote the time. Then at step k, the transition matrix is simply the k's power of some unitary matrix. So that is change number 1. Change number 2 is we cannot take U to be an arbitrary unitary matrix. Now it has to respect the so-called locality. And what do I mean by that? It means after each step, you can only move to one of the neighbors. So the walker cannot jump too far. Okay. So this means whatever you construct, it must respect the adjacency of the graph. So naturally, one may want to construct U by weighting your adjacency matrix. For example, you want to change these numbers and see if you can get a unitary matrix out of it. But this is a counterexample to that possibility, because you can see no matter how you weight these edges, you can never make the first column and the last column orthogonal to each other. Right? So this shows there's no unitary adjacency matrix for P3, and this idea in general is infeasible. So in 2004, Simone Severini has a nice paper on which digraphs can admit a unitary matrix. And he has some nice characterization. So if you are interested in this characterization, I suggest you take a look at this paper. Okay, so how should the quantum worker respect both unitarity and locality? So here's the solution. Instead of letting him working on the vertices of the graph, I'm going to let him work on the arcs. Okay, so here I draw my K4 a little bit unusually. I still keep all the 4 vertices, but every edge is now replaced by 2 arcs with opposite direction. So I have in total 12 arcs for the graph. And the state of this graph is now a complex value function on the arcs, or in other words, a vector of length 12 indexed by the arcs whose entries are complex numbers. Okay, and we insist that vector to be unique. So here's example. The blue arc gives me 1 entry in my state. So it's a complex valued function that assigns 1 to the arc 0, 1 here. And the other arcs all receive 0. Not sure if you can see my screen. Okay. So let's take this as the initial state of my quantum work. Now I need to tell you how the system evolves. So in each step, there are 2 sub-steps. The first step is called a coin flip. This is just similar to a coin flip in a classical random walk. So in a classical random walk, the worker flips the coin to determine which direction he wants to go to. Okay, so that coin introduces some randomness. In the quantum case, we define a quantum coin that introduces some quantumness. And that coin now has to be a unitary operator. So basically what it does in this specific model is it maps every arc to a linear combination of all the arcs from the same outgoing vertex. So for example, here, before I was standing on this arc, so from 0 to 1, so the tail of this arc will be 0, right? And after this coin flip, I'm now everywhere, like on all these arcs starting from 0. Okay, so this new state is -1/3 here, 2/3 here, 2/3 here, and 0 elsewhere. And because the coin is unitary, that means my resulting state at this stage is still a unit vector. And this is called the Grover coin because it has a very specific structure. If you compare this new state to the old state, you will see that the number it assigns to the original arc is -1/3. And the number it assigns to any other outgoing arc of 0 is 2/3. Okay, so we can easily generalize this to other initial state if we start with some arc. Okay, so that is the first half of my 1 step. We are not done yet. Now, if you keep flipping a coin, then we will see we are too localized at these outgoing arcs of 0. So the quantum work can never propagate to other vertices. So now we need a different operator that pushes the worker forward. And that's gonna be the arc reversal operator. So it simply sends the number at each arc. So before it was these 3 arcs to their opposite arcs. Okay, so now I have -1/3 on the opposite arc to my original arc 0, 1, and 2/3 on the other incoming arcs of 0. And this will be my state after 1 iteration. U denotes the unitary matrix. So if there's any question about this model, now it's a good time to ask. All right, so with that, we are ready to write down our transition matrix. Each column tells me what I will get if I start with that column index. So for example, here, I see exactly the same vector on the previous slide. Let's pick another column to check if my U is correct. So take the column 1, 2. Then I expect to see a -1/3 on the opposite arc of 1, 2, which is 2, 1. Okay, and I expect to see a +2/3 on all the other incoming arcs of 1, so 0, 1, and 3, 1. Okay, and it has to be the incoming arc of the tail of my original arc. Okay, so in that way, you can figure out every column of the transition matrix. But now I invite you to look at, instead of the columns, but the rows of this matrix, because I think it has a neater combinatorial meaning. So let's look at the first row. I see it's not complete. I cannot put everything in the slides, but believe me, every row has only 3 non-zero entries. And moreover, these entries are all indexed by what? So for the first row, they are indexed by the outgoing arcs of 1. Okay, and I can pick another row, let's say this guy. If I start with 1, 0, then the columns will be indexed by all the outgoing arcs of 0. So this is like moving forward one step in the line digraph. And we can view U as a weighted adjacency matrix of the line digraph. Okay, so let me explain a little bit what I mean by line digraph. Here I give you a smaller graph, K3, on the left-hand side. Again, I replace each edge by 2 arcs. On the right-hand side, this is a line digraph of K3. So the vertices are all the arcs from the left-hand side. And an arc AB is adjacent to CD if the tail of the second arc is equal to the head of the first arc. In other words, if B is equal to C. Okay, so for example, here we see 1, 0 is adjacent to 0, 2. But mind you, this adjacency is not a symmetric relation. So 0, 2 is not adjacent to 1, 0 because 2 is not equal to 1. That is comment number 1 about this adjacency. Comment number 2 is we do see some edges here, or diagonals, because AB is always adjacent to BA. Okay. Okay, so now I can give a more combinatorial definition of the transition matrix. In this talk, I will focus on regular graph only. For any regular graph, U is equal to 2/k times the adjacency matrix of your line digraph minus R. K here is the valency, and R is the permutation matrix that maps AB to BA. So if K equals 3, then I will see 2 distinct entries, 2/3 and -1/3. And that is going to agree with my previous matrix. So you will see -1/3 in the support of that R matrix, and you will see 2/3 in the other support of the line digraph. Okay, and people sometimes refer to this work as the Grover work because the famous Grover search algorithm can be viewed as a quantum work on the complete graph with loops. So here the question is, we have some complete graph and there's one vertex that is marked, but we don't know where it is. So we want to find that vertex with as few queries to the oracle as possible. Okay, and according to Grover, this is what we can do. We will start with a uniform state over all the arcs. So, okay, so all one vector up to some scalar. And then I'm gonna apply one step of my Grover work. And then ask my oracle, have I landed on an outgoing arc of the red vertex or not? So that oracle is gonna answer me yes or no. Okay. After that, I apply another iteration and ask the oracle again. So I can do this many, many times. And Grover's algorithm says that after about square root n steps, where n is the number of vertices, I'm gonna concentrate, the final state is gonna concentrate on all the outgoing arcs of the red vertex only. So that means with certainty, I will find out that marked vertex. Now, in a classical algorithm, it takes O of n steps to find this market vertex. So that is a quadratic speedup. Okay. So there was some background about discrete quantum works. I have showed you a model called Grover work, and I have showed you some application. And also, hopefully, I have convinced you a discrete work on the graph, let's say K4, is different from the continuous work on the same graph. Okay, but now I want to show you, I can still view the discrete work as a continuous work on some other directed larger graph. And here's what I think. So in the continuous work, the idea is it's almost like I'm taking the exponential of a graph to get a work. And then I ask for which graph is the work interesting, right? But now in the discrete work, I'm going to take the logarithm of the work, which is I times Hermitian matrix. Then the Hermitian matrix will have an underlying digraph. So my question is, for which discrete work will this Hermitian matrix and its underlying digraph be interesting? Okay, so maybe your first question is, how do I take the logarithm of a matrix? Well, my answer is, if you know how to exponentiate the matrix, then you know how to take the logarithm. If I know the spectral decomposition of U, which is a big if, but I will explain to you how to find this. But if I know the spectral decomposition, then I know all these lambdas, the eigenvalues, will be on the unit circle. Right? Then when I take the logarithm of U, it's equivalent to taking the logarithm of all these eigenvalues and combine it with the eigenspace f lambda. Okay, so in this way, I can take one logarithm of U, and I say one because this function, it has many branches, so it doesn't have a unique value. But we can make some choice. For example, I can restrict the angles to those between zero, sorry, let's say between minus pi and pi. Okay. Moreover, in the Grover work, we know U has real entries. So that means it has 3 types of eigenvalues, 1, -1, and other complex eigenvalues that come in conjugate pairs. +1, -1, so e to the plus minus I theta. Okay. So how do I translate into my edge matrix? Well, the logarithm of 1 is 0, right? So it doesn't contribute any term to edge. The logarithm of -1 is I pi, and that explains this term here. Now, for all the other complex eigenvalues, if they come in conjugate pair, then they should, so their angle should be opposite to each other. Moreover, their eigenprojections must also be conjugate pairs. So in this way, I can group all these complex eigenvalues as a linear combination of the differences here. So I can just pick all the angles that live strictly between 0 and pi. And that way I halved the number of terms in the sum. Okay, so with that choice, let's look at the edge matrix of the previous work. So here I have rounded up every entry to second decimal places. And I don't know what you think about this matrix. Is it nice or is it terrible? So to me, I have a mixed feelings. It's not too terrible because I can expect some symmetry here. For example, these two are equal. Okay, so that is too far away, but I mean, there's some pattern, so it's not too terrible. But it's also not very nice because one, this is full, it's too crowded. So that means the underlying digraph will be a complete graph with loops, okay? And 2 is the entries are a mixture of real numbers and complex numbers. So this means if you look at the underlying digraph, then we have to distinguish between the edges and the arcs. So Crystal has a paper on Hermitian matrices of digraphs. So there she puts a plus minus I think plus minus I and some real entries, I think is 1. And I don't know if minus 1 is there or not. So we can view this as a generalization of that matrix. So it's possible to analyze this matrix, but in general, I don't think it's the best choice for this model. But we should expect that for any logarithm of the unitary matrix, because here it suggests that we may have a symmetric part, right? And here it suggests we may have a Hermitian part. Okay, so my solution to those two problems, too crowded and has a mixture of complex and real entries, is to look at a different logarithm. So now instead of looking at the logarithm of U, I'm gonna look at logarithm of U squared. What this does is it upgrades all the eigenvalues in the sense that the +1 eigenvalue now becomes +1, -1 eigenvalue squared to then +1, and the plus minus I eigenvalue squared to -1, and all the other complex eigenvalues, so plus minus I theta now becomes plus minus 2I theta, but they still remain complex. Okay. So with that change, this F minus 1, it used to be the -1 eigenspace of U, but now it gets merged into one eigenspace. That means logarithm of U squared, it doesn't contribute anything. So I can cross that out. And if I insist that, if I make sure plus minus I is not the eigenvalue of U, then that means I can just scale the remaining terms by 2. So this will be my new Hermitian matrix, which consists of only this Hermitian part. Let's see how this idea plays out. Here, I present to you the logarithm of U squared of my previous work. It looks so much neater. It's not too crowded. There are so many zeros in each row, and it only contains plus minus on entries and up to a scalar. I mean, it's a skew symmetric adjacency matrix of some oriented graph. So I think this is much nicer, and I can show you the oriented graph here. Does anyone want to guess what this graph is? So yeah, I don't know if this is the first time you saw it, but I'm too familiar with it because 2 years ago when I was still a PhD student, I constructed a new quantum walk called vertex space walk. So it depends on an oriental embedding of a graph. So you take two partitions of the arcs, one according to their tail and the other according to which phase they lie in this embedding. And at that time, I was also interested in the logarithm of U, but I didn't have much data about oriental embeddings. So I kept looking at the regular embeddings of the complete graphs. And it turns out for all those embeddings, the logarithm has exactly the same form. And I got exactly the same oriented graph. And then I was very confused by the relation between this oriented graph and the underlying embedding. But Maria, who was a URA at that time, she proved that all these oriented graphs have the same skew adjacency matrices as the line digraph of the complete graph, which is a very interesting result. So I was very surprised to see the same graph show up again in a different model. But I should comment about the difference between this graph and the line digraph. So I say they have the same scale adjacency matrices because in the line digraph, you will see these diagonals. And they contribute to the symmetric portion of your adjacency matrix. But when I take the difference between A and A transpose, I kill off all these diagonals. And that's why this remaining graph is such a nice oriented graph. So there's a difference. You can call this the diagonalist graph, or I'm lazier, so I just call it the global digraph because it comes from the global work. Okay. So how should I prove that result? How should I show that the groupable on a complete graph is equivalent to a continuous walk on its line digraph? So to understand the global digraph, I must understand that H matrix. And to understand the H matrix, I must understand those FR. And to understand those FR eigenprojections, I need to know how to spectral decompose my transition matrix U. So here I'm going to present another definition of U. So I'm going to write U as a product of two reflections, showing that U lives in a nice algebra. So we can diagonalize U based on the invariant subspace of these two operators. Okay, so to that end, I need to introduce two incidence matrices called tail arc incidence matrix and head arc incidence matrix. And you can probably guess what they are from the name. So let me explain DT. So in DT, the rows are indexed by the vertices. Let's say A, okay? And the columns are indexed by the arcs, X, Y. So this is a fat short line down matrix. And we will see a 1 in an entry if the row index is equal to the tail of the column index. So if A is equal to X. And you can define DH similarly, just replace the tail by the head. Okay, so these two matrices interact nicely with each other, as well as with the arc reversal matrix. So I will list some properties here. The first one is this. So if I let this be D, what happened? If I let this be DT and heated by the standing up matrix, DH transpose, then I get a huge matrix indexed by the arcs. Okay, and what are the entries of this matrix? Well, we're really looking at a row of this DH transpose, let's say AB, and a column CD of this DT matrix, and see if they overlap with each other. But these two rows and columns will overlap only at the position X, where X is equal to B, because it needs to agree with the head, and X is equal to C because it has to agree with the tail. In other words, we see a 1 if and only if E is equal to C, or those two arcs form a dipath or a diamond of length 2, A, B, C, D. Okay, so let's say in DH transpose DT is precisely the adjacency matrix of the line digraph. The second property, if you think about what R does, why is my screen so weird? Okay, that's better. Okay. If you think about what R does, it simply swaps the tail with the head of an arc, right? So when I hit DT by R, I should get DH, and vice versa. So with the first two properties, I can simplify the right-hand side. So it's actually 2 over K R times DT transpose, which becomes the H transpose, DT minus R, or 2 over K by the first property, A of the line digraph minus R. But that's exactly the definition we started with. Okay. Now if you multiply DT by its own transpose, then you can see this is counting the degree of some vertex if the row index agrees with the column index. So that explains this identity. And if I multiply DT by DH transpose, then what do I get? Now I have a lying down matrix multiplied by a standing up matrix. This is dt, this is dh transpose. So I'm looking at a row indexed by some vertex A and a column indexed by another vertex B. And they will overlap in this position if x is equal to A and y is equal to B. So in other words, the AB entry of this product is 1 if and only if A is adjacent to B. So that product coincides with the adjacency matrix of X. And you can switch the order and show that the other product is equal to that too. Okay, so with all those identities, I can express my U squared as a product of two reflections. So here I can combine the first three terms, and R together with dt transpose becomes EH transpose. And by one of the properties, we know this product is actually a projection onto a column space of DH transpose. And this product here is also projection. Now, in geometry, we know twice the projection minus the identity is a reflection. So actually, U squared is a product of two involutions. This means U squared lives in some diffusion group, and we can find the eigenspaces of U squared by looking at the invariant subspace of these two projections. And here is some technical lemma from linear algebra. So in general, if V is a product of two reflections, and let P and Q be the projections, then the state space is a direct sum of PQ invariant subspaces whose dimensions are at most 2. Okay. So the one-dimensional invariant subspaces are easy. They are precisely the eigenvectors of V. And if such an eigenspace is either fixed by both projections or killed by both projections, then they give rise to the one eigenvalue of V. If it's killed by one but fixed by the other, then we have eigenvalue -1. What about the two-dimensional subspaces? Well, they all come from the sum of two vector spaces. And each of these invariant subspaces will give us eigenvectors of V that corresponds to non-real eigenvalues. So let me be a bit more specific. Because P and Q are projections, they are positive semi-definite, so I can write them in this outer product form, where M and N have also normal columns. Now, the trick is to look at this product instead. So in general, this is gonna have a much smaller size compared to P and Q, but it carries almost the same spectral information as V, in the sense that every eigenvalue of this smaller matrix called discriminant matrix can be lifted to eigenvalues of V, and the eigenvectors of this smaller matrix can also be lifted to a longer eigenvector of V. So I won't tell you the details about the derivation, but just apply the result to our U squared. So here, M is my DH transpose, and N is my DT transpose. So the discriminant matrix is really this guy here. But hey, we know exactly what these products are, right? They are just adjacency matrix of X. So the upshot of this result is the eigenvalues, eigenvectors of my underlying graph can be lifted to those of U squared. And I will show you the spectral correspondence in a little table. Again, I'm assuming my graph is regular. So say it has values k, then all the eigenvalues lie between -k and +k. So I can write them as k times cosine theta here. Now, if this eigenvalue is neither plus minus k nor 0, then it determines the real part of a complex eigenvalues of U squared in this way. Conversely, every non-real eigenvalue of U squared also come from an eigenvalue of X that does not lie in this set. Okay, so we kind of have a one-to-one correspondence. What about the eigenspace? Well, for every E lambda of X, we can leave it to the eigenprojection of U squared in this complicated form. So if you expand that, you will see 4 terms. Some of them are complex, some of them are real. So it's not a beautiful expression. But for our purposes, we only care about the difference between f theta plus and f theta minus. So after some calculation, you realize that boils down to basically this matrix. So 2 comments about this S lambda. First, it's real because ET is real, DH is real, and the eigenspace for the eigenprojection for my underlying graph is also real. And the other comment is S lambda is skew symmetric because we have some matrix subtracted by its own transpose. Okay, so let's keep that formula and take a closer look. On the left-hand side, I have a huge matrix indexed by the arcs. But on the right-hand side, I have a smaller matrix indexed by the vertices. And this gets pre and post multiplied by 2 incidence matrices. So that means there are a lot of repeated entries in S lambda. To be more specific, if I zoom into the ABCD entry, okay, then here I'm looking at the entry of E lambda indexed by the tail of my first arc and the head of my second arc. And the second term here is just E lambda indexed by the head of the first arc and the tail of the second arc. So every entry in S lambda is really just the difference between 2 entries in E lambda. Okay, so let's apply this formula to our complete graph. What do we want? We want to look at the eigenvalues that are neither plus minus valency nor 0. And the only choice for Kn is -1. So we just need to take care of E minus 1. And we know E minus 1 is a linear combination of I and J. So by this formula, the only way for left-hand side to be non-zero is to ask A and D to coincide and B and C to be different, or to let A and D to be different, but B and C to coincide. But this is precisely when you have, I guess it's CD, AB, or AB, CD. Okay, so there's a non-zero entry if and only if either CD is adjacent to AB or AB is adjacent to CD in the underlying digraph indexed by the arcs. So that is exactly the adjacency matrix of the line digraph, skew adjacency matrix. Okay, so what about other graphs? The complete graph is a special case because we only need to look at one subspace. In general, a graph will have a lot of eigenspaces, and that means I shouldn't expect an unweighted digraph. But could it be possible that every eigenspace contribute one weight? That is not true. So take the Peterson graph. It has 3 eigenvalues, one of which is 1. So if you look at E sub 1, because this is a strongly regular graph, every row has 3 distinct entries. So that means when I take their differences, I'm gonna see plus minus 2 and plus minus 4. So that is already a weighted oriented graph. And in fact, this is what happens when I lift E sub 1 to S sub 1. But you see, it's still quite sparse. So maybe I can still spot some graph by looking at different weights. So as it turns out, all the plus minus 4 entries actually correspond to the line digraph of the Peterson graph. So this is nice. What about the plus minus 2 entries? It turns out they correspond to not the line digraph, but its second distance digraph. And what do I mean by that? I mean exactly what you think it is. If you take a digraph, then the ith distance digraph will have the same vertex set as your original graph y, and two vertices u and v are such that u is adjacent to v if and only if the distance from u to v in the original digraph is I. Okay, so here we have a beautiful picture of the second distance digraph of the line digraph of Peterson graph. I'm sure you can verify it very quickly. Okay, so what do we know? We know in the Pearson graph, this logarithm is a weighted union of this graph and its line digraph. Does this result generalize to any strongly regular graph or even distance regular graph? So I don't know, but I have to start with some test, right? So the first test I took was the Paley graph of order 9. And then here's what I do. I'm doing exactly the same thing as before. This graph has 3 eigenvalues, one of which is 1. So I look at S1. Turns out S1 also has 2 different entries. So I can partition them into 2 skew adjacency matrices based on these entries. In that way, I obtain 2 oriented graphs. And then my wishful thinking is maybe I can compare them to the distance digraphs of the line digraph and see if there is isomorphism between them. It turns out they are not isomorphic. So none of these oriented graph obtained from weights of the S1 coincide with the distance digraph of line digraph of X. So that really broke my heart for like 5 minutes until I realized why it doesn't work. Because the Pearson graph is very nice in the sense that it has girth 5, but the Paley graph has girth 3. That means when you look at the symmetric adjacency matrix of 2 distance digraphs, their entries overlap with each other. So when I take the sum, there's a cancellation. Okay, so that means I cannot get this oriented graph by simply looking at the weights. But my little conjecture is still true. I can still write my Hermitian matrix S or the S lambda as a linear combination of the skew adjacency matrices of these distance digraphs. I'm going to show you this holds for not only strongly regular graph, but any distance regular graph, provided they have invertible adjacency matrices. So here is some notation. X is the distance regular graph. AI is the adjacency matrix of this I's distance graph. And we know all these AIs form an association scheme. In particular, there are these intersection numbers so that this identity holds. This PIJL tells me the number of vertices W at distance I from U and at distance J from V, given that U and V are at distance L. And we also know that each eigenspace of a E sub lambda is a linear combination of these AIs. And those coefficients are determined by these dual eigenvalues. So now, by this formula of S lambda, we know that its entries only depends on 2 things. 1, the distance between A and D in X, and 2, the distance between B and C. But how does this translate into distance in the line digraph? Well, if A, B, and C, D are different, then you can show that this is actually the distance. I mean, it's not equal to, but it determines the distance between 2 arcs CD, AB, or actually it's distance from CD to AB, and that determines the distance from AB to CD. Okay. Okay, so let me be more specific about the relation. Given AB and CD are distinct from each other, then the distance from AB to CD in the line digraph is exactly 1 more the distance between B and C in the original graph. And the proof is easy. It consists of 2 steps. First, every path from B to C of length L gives rise to a dipath of length L plus 1 in line digraph, because these two endpoints are not equal to each other. So that shows one inequality. For the other inequality, we take the shortest dipath in the line digraph from AB to CD. And let's say it consists of a sequence of these arcs. Then my claim is all the heads here must be distinct from each other, because if they are not, then we will see two arcs coming into the same head, UJ. Okay, but then I can just remove the entire portion between these two arcs to create a shorter dipath. That forces a contradiction. So that shows this inequality. But if AB and CD are the same, then we don't have this identity, because on the left-hand side, I will get a 0 because they are the same. But on the right-hand side, I will get 1 plus 1, which is 2. And the argument fails precisely at this step, because here, instead of getting a dipath, we get a cycle. Okay, so combining these two situations, I have a formula about distance in the line digraph in terms of the distance in the original graph. And that translates into a connection between the adjacency matrix of a yi, the ith distance digraph of my line digraph, and these adjacency matrices of my xi's. So in general, if you want to find a yi, then you're going to a of x sub I minus 1. And then leave it using these two incidence matrices. But we have to be cautious when I is equal to 2, because if two vertices are at distance 1 in the original example, then there are two possibilities for the distance from one arc ending at one vertex to the other arc starting with the other vertex. Okay, so this is the only case we need to be cautious. Okay, so that formula gives us a lot of useful information about the distance diagrams of a distance regular graph. So one of them is all these A's sum to the O1 matrix. And that's a simple fact that when you take the sum, you get DH transpose JDT, but this DH transpose and DT has constant row sum column sum. And you can work out this in fact equal to J. And the second property is the line digraph of a distance regular graph is again distance regular. And what I mean by that is if you take any arc AB, CD, and suppose the distance from AB to CD is L, then any third arc XY that are at distance I from AB and from which CD is at distance J depends only on IJ and L. So in other words, I have A of YI, A of YJ lives in the span of A of YL. But that translates into this condition, or because we know this is equal to AX or AI. So that just means DH of A sub something DT lives in the span of DH A sub something DT. And the third property is this matrix as lambda that we are interested in lives in the span of the skew adjacency matrix of these YIs. And that's an even simpler result because E lambda is just a linear combination of EI. And we know S lambda is this guy minus its own transpose. And finally, we can verify all these skew adjacency matrices commute with each other. And that follows from a similar argument to bullet point 2. Okay, now we are ready to factor U squared. So here's a setup. Take a distance regular graph X. Suppose it has invertible adjacency matrix. Then I know U squared can be written as exponential IH for some Hermitian matrix H. Now, because X doesn't have 0 as an eigenvalue, that means U squared doesn't have -1 as eigenvalue. So my H has a synchronized form. So it lives in the span of S lambda. Okay, and we know each S lambda lives in the span of SYI. And because all these SYIs commute with each other, that means I can write U squared as not just exponential of the sum of SYIs, but the product of exponentials of each SYI. So that shows a discrete quantum walk. The second power of that transition matrix factors into at most D continuous quantum walks. And the important thing here is not that we are able to factor U squared, but we can factor it into commuting continuous quantum walks. So if I raise the left-hand side to any integer power, then on the right-hand side, I simply add K to each exponent. So just a little remark. In this decomposition, we see D terms, but it's not guaranteed that all these distance digraphs will appear. For example, in the 3 cube, when you take the logarithm, you will only see the distance, so the second distance digraph of the line digraph of Q3. Now we have 2 ways to interpret the probability or the mixing matrix of a discrete walk. So here I show you the square of U and actually not square of U, but the mixing of U, mixing matrix of U squared. These shades denotes the probability that you will land on a particular arc if you start with an arc. So you see it's still a very sparse matrix because of the locality condition. After 2 steps, your quantum walk cannot move too far away. Okay, so on one side, I have this matrix. But on the other side, I know this is equal to the mixing matrix of IH, where H is a weighted union of the line digraph of the Peterson graph and its distance digraph. Right, so that means in the continuous walk, somehow I can find the time so that it exhibits this weak sense of fractional revival. So if I start with a particular vertex, then at some time I'm gonna concentrate on only a few vertices. So that is a very cheap way to create this weak sense of fractional revival in continuous quantum walks. So here are some projects that we can look at after finding out this relation. So the first one is, how does the property of discrete walk translate into properties of the continuous walk? We have an infinite family of circular graphs that exhibit discrete perfect state transfer. So that probably translates into some multiple state transfer of a continuous walk on the oriented graph. And of course, we can also study relation the other way. So I think Tino has a paper on oriented graphs, and Sabrina has a thesis about the same topic showing there's a multiple perfect state transfer on oriented graphs. So maybe they will translate into multiple arc state transfer in the discrete walk. And finally, in this example, we are able to factor the global walk nicely because the distance regular graph have very nice item projections. But there are some Cayley graphs whose projections are also nice. It comes from characters, and maybe there's some group theory result we can use. So a third line of research is to look at if we can factor global walks on some other nice graphs. So that's what I want to talk about. Thank you.
Thanks, Harmony. Do we have any questions for Harmony? Okay.
Sorry. So does it seem like it would be difficult to generalize just from distance regular to say association schemes or something like this?
I think you can still generalize, but it probably doesn't have anything to do with the distance digraphs then, because the reason why you can translate is that E sub lambda in the distance regular graph, it only depends on the distance between A and B and C and D. So they translate into distance from arcs to arcs. But if you take other association scheme, I'm sure you can still factor it nicely, but there will be a different interpretation of the underlying diagram.